So I'm going to talk about bias in artificial intelligence today, which is a very important but also very complex topic. Not only is it complex from a technical perspective, it's complex from an ethical perspective and, in fact, a practitioner's perspective as well. So I'm going to talk about it. I'm not assuming much knowledge here of the topic of AI, of machine learning. There will be some elements of this presentation that are quite technical, but I'll try and explain them as much as I can. So first of all, let me tell you why I'm here and why I'm involved in this topic. So I'm Chief Technology Officer at a company called Dragonfly, which consults and builds products. Our consulting has specialized around the verification of quite complex systems. Initially in investment banking, working with quantitative models, ranging through to projects to replace ATM networks and things like that. But why this is relevant is we started building a product a few years ago, about 4 years ago, I think. And that product does something quite interesting. It allocates work to people within software engineering teams. So it maybe if some kind of defect is detected in software or some task needs to be carried out, it will use knowledge it has about the team and about the software in order to determine the correct person to execute the work. Now, at this point in time, when we were developing the machine learning, I became aware of these issues around ethics and bias. And it seemed to me that allocating work to employees was something that we should get right in this context. And indeed, the EU's AI regulations, which are currently proposed, and I'll talk about a bit later, specifically call this out as a high-risk use case that needs to be regulated. So I picked up, I went to a few seminars, I read lots of papers. The problem I had here is I had to read 20 or 30 articles from the literature to understand the topic. And I still didn't have a consistent view of what I should do about it. And the reason that's an issue is nobody who is actually in the software engineering field or systems engineering and is busy implementing projects is going to go and read the literature. Typically, professionals who work in implementation of systems will go through training courses and will adhere to technical and professional standards. So I then started looking at the technical standardization area, because technical standardization is really the root of a lot of processes and techniques that are used in industry. And it's used a number of ways. First of all, technical standards drive training courses. Technical standards also drive the implementation of legislation. So again, the EU AI regulations have specifically called out that as standards are approved by the European Union, harmonized standards, they automatically become effectively law. Standards are also used to enforce things through the supply chain. So it's quite common when you're bidding for work to be asked if you adhere to certain technical standards on security or other things. Now, I started getting involved in technical standardization with both IEEE and ISO IEC. So these are international standards organizations that include technical representatives from all over the world. And I ended up taking a leadership role on building the technical report, the draft technical report on the screen, 24027, which is all about bias in AI systems and AI-aided decision-making. I'm also very involved in a number of other areas. I work very closely with the British Computer Society, and I have a podcast called Fuzzy Quality, where I explore all sorts of technical topics around AI and quality, including bias. Now, I tend to fit into that kind of technical level, a bit below the high-level ethical principles, trying to get into the detail of what should people do on a day-to-day basis on the ground to avoid some of these issues. So in this presentation, I'm going to take you through some of the background of AI and bias, but I'm going to specifically tell you what can be done at different stages of the life cycle in order to mitigate bias and develop systems that are ethical and legal. So let's start with the perennial question, what is artificial intelligence? So this definition suffers from something called the AI effect. Every time someone agrees a definition, the field moves on. Going back to the 1950s, Alan Turing was defining AI based on the Turing test, which involves somebody being a blind conversation with an AI natural language processing bot and a human. And if the person is unable to tell which is AI, then the AI passes the test. Now, obviously, our definition of AI has progressed significantly since the 1950s, as has the technology that we have. And the reason that we have such a ubiquitous uptake of artificial intelligence at the moment is not so much actually due to the techniques, but due to the increase in data that's available in the world, as well as the increase in the availability of computing power. Techniques like neural networks have been invented in 1958, but really have taken off in the 2000s. So the prevailing definition of artificial intelligence in international standardization is the one on the screen. This is taken from ISO IEC Draft International Standard 22989, which defines foundational concepts of artificial intelligence. So the definition is a set of methods or automated entities that together build, optimize, and apply a model so that the system can, for a given set of predefined tasks, compute predictions, recommendations, or decisions. Now, bias can exist in various types of AI systems. So AI tends to be divided into symbolic and sub-symbolic AI. Symbolic AI is expert systems and things that use formal logic. Sub-symbolic AI is mostly machine learning. Now, bias in particular affects machine learning, but it can affect other AI techniques. Essentially, the knowledge or the model within the AI system is built through a learning process, and the data that the system is exposed to during that learning process drives its accuracy and drives unwanted bias issues. There are other ways that you can introduce bias into a system other than data, but that is the primary one. One really interesting thing here is the off-qual algorithm that hit the news last year. So predicting people's school leavers' grades and exam grades. So this wasn't an AI system, but it was using statistical techniques. And the issues that it suffered are exactly the same issues that we're talking about for bias in AI. One of the interesting things about the proposed European Union regulations is they include statistical techniques within their definition of AI. So therefore, a spreadsheet could easily be in scope of that regulation. And personally, I think that's a good thing, because what we're trying to regulate here is primarily a lot of those statistical techniques. Is it a real problem? It is. I mean, I could put hundreds of headlines on the screen here. I picked three. So on the top left, recruitment. So AI recruitment is an interesting one because there are companies that market it as removing bias from the process, but yet there is clearly lots of opportunities for bias to exist in AI recruitment tools. And again, that's one of the high-risk use cases in the proposed EU AI regs. In the bottom left, machine bias. So there is software used in the US called Compass, which is used to help inform judges about the risk of reoffending. And that then helps them decide whether people should be put on probation. And that's been demonstrated to be biased. And what's interesting is that's partially, at least partially, because historically, the way that people have ended up in prison and things that they've done, the societal bias from the disparity in the way people are potentially treated by the police is then being used to predict how to handle future criminals. So really interesting example. In the top right, a UK example relating to UCAS. And this is actually a natural language processing engine. So they use, when people submit an application to UCAS, the free text areas a pass-through algorithm which tries to detect a fraudulent application, and your ethnicity affects that. In none of these examples is race, gender, an input to the algorithm, but yet we see bias that affects certain groups. This is a very real problem, which is why there's focus on regulation. So what is bias? So there's a lot of different views on this. Someone might say this is a statistical thing. It's a systematic difference between true or accepted values and measured values. You might say it's a particular tendency, trend, or inclination or opinion that's preconceived from a psychological or sociological point of view. And the definition that we are adopting within the international standards community is sort of a combination of them. It's a systematic difference in the treatment of people, objects, or groups in comparison to others. Now, a few words in there that I'll pull out. Systematic, this can't just be a one-off. Difference in treatment. Treatment can mean many, many different things, but essentially we're talking about the predictions and recommendations that come out of the system. It can affect objects. It is not simply something that affects people, although we are obviously much more concerned about the impact on people rather than whether a traffic light system is biased against red cars. And finally, it can only be demonstrated in comparison to the treatment of other groups. So this is where we're kind of getting to on the definition of bias. Neither the definition of AI nor the definition of bias that I'm showing on the screen is final, but they should be in the next few months as these standards are published. Another complexity around bias is we can use it to describe causes. So I might have sample bias in my training data, or I might have cognitive bias in my system designer. But I can also use it to describe outcomes and outputs, so someone being treated differently. So for clarity, we tend to refer to unwanted bias when we talk about outcomes. But essentially, we always try and put a word before bias, some kind of qualifying word, because the word on its own is a bit overloaded. Now, how does this relate to fairness? So in fact, in the 2.5 years I've been working with international experts on this topic, the most contentious issue has been understanding this relationship with fairness. Because based on the definition of, that I put on the screen of bias, treating different groups of people differently, you can also say that that bias is necessary. If I have a recruitment system that is hiring professors, I might want a bias towards PhDs or certain qualifications, or I might want a bias towards underrepresented groups. So bias isn't necessarily unfair. It can be fair and it can be unfair. You can also introduce positive bias to compensate for negative bias. So for example, again, talking about hiring, you might introduce a specific bias towards gender in order to compensate for historical societal bias. And of course, then you get into talking about things like affirmative action, which is one of the reasons this is such a difficult topic to agree on at a technical level. Additionally, fairness is completely context dependent. For example, in the EU and the UK, it is unlawful to price insurance differently for men and women, whereas in the US, it's normal. So there is no kind of international standard for fairness. There is 21 different mathematical definitions of fairness, and one could even say the fairest system is a random number generator. So it becomes very, very complex understanding that relationship between the two. Additionally, one problem with bias and fairness is there are trade-offs. So you're rarely able to get to a completely unbiased system. You need to have things like thresholds and try and come up with the most balanced system that you can. Some of the examples of the type of impact on people that could be called unfair resulting from AI systems include unfair allocation. So where a system unfairly extends or withholds opportunities or resources in ways that have negative impacts on some parties. Unfair quality of service. So let's say the facial recognition system on the door to my office building doesn't work for me, doesn't work for people with my skin color. It's actually the opposite is true. But that is an issue. If systems don't work well, and that then impacts people's ability to get services or even access their place of work, that's an issue. Stereotyping and denigration can occur as a result of systems, and also over or underrepresentation. AI can overrepresent some parties compared to others, or fail to represent their existence. Bias is one of many things that can impact fairness, and it's not the only thing. I talked about regulation a little bit, so absolutely, machine learning and bias is covered by GDPR. But when you are processing people's personal data, which you often are with AI systems, you have a duty to ensure accuracy. And if you go to the ICO, the Information Commissioner's Office's website, they will specifically talk about bias when you are using AI systems that use personal data. You also have to ensure that you aren't infringing upon people's fundamental rights generally. So if, in the examples I just gave of unfairness, that would mean that those systems fell inside the scope of GDPR. So there is limited enforcement of this regulation at the moment, unfortunately. I'm only aware of one example in the EU of AI systems resulting in large fines. However, it is something that's taken quite seriously. When I speak to companies like Amazon, facial recognition companies that are big in the financial services sector, they're working really actively with the Information Commissioner's Office in something called the sandbox. So a sandbox is something where you've got a system, you don't know if your accuracy is high enough. Is 98% accuracy on that facial recognition system on my office door good enough? What about if it's 90% for people with certain ethnic backgrounds? Is that okay? So the sandbox is an area where companies can take those problems and work through them with the Information Commissioner's Office. You're fundamentally not allowed to put a system live that is using personal data and AI unless you have assessed the risk and documented all of your processes. There's also various initiatives within the UK public sector. Because the GDPR doesn't apply in the same way to the public sector in the UK, there are various codes of conduct that would require you to do many of the steps that I'm going to talk through. And we also talked about the proposed EU AI regulations. So these have been signposted for a long time by Ursula von der Leyen. And we are now at the stage where there is a proposed text in front of the European Parliament. Now, like GDPR, this is an extraterritorial regulation in scope, which means that it will affect any company anywhere in the world that is using EU citizen data with these systems. In fact, the regulation can be described as essentially consisting of three components: a requirement to do risk assessment and management, a requirement to do thorough verification and validation, and a regulatory framework to enforce all of that, including a CE mark upon systems. I don't know how you can actually physically put that mark on an AI system, but I guess we'll find out. Over the next probably 2 years, this regulation is going to be debated and put into effect. However, much of the detail will come from the technical standards. So the EU's standardization body, CENELEC, has just formed a joint technical committee to start work on all of those standards. My big fear, of course, is that the law comes into effect before we technically know how to comply with it and before industry is able to comply with it. So let's get on to where does bias come from? And often the answer is cognitive bias in people. There's a few examples, there are hundreds of cognitive biases that people can have. Some of the key ones, though, are described on the list. The first one is societal bias, although that really comes from other biases that have become manifest in society or organizational policies. One of the biggest issues with societal bias is it is reflected in data. If you look at the number of computer scientists of each gender, you will see a skew. And therefore, and whilst that skew may be decreasing over time, without compensation for that societal bias in the training data set, what you'll see is the AI essentially picks up that bias and replicates it. It's like money laundering for bias. Now a machine's saying it's okay. So group attribution bias is one where you assume that what's true for you is, or what's true for one individual is true for all other individuals in that group. Confirmation bias is when your hypothesis is confirmed because you believe it, essentially, and you intentionally or unintentionally interpret information that confirms what you already think. Non-response bias is when people don't respond to things like questions and surveys. So this might be because of people's age, for example. People in a certain age group might not use technology as much, so they might not be represented in data sets. Or the example on the right, yes, certain types of people do surveys. We also have in-group and outer-group bias. So in-group bias is about a partiality to your own group. Out-group bias occurs when you see people that aren't in your group as kind of all similar. You don't see the difference between different groups and different people as much. And then finally, we have requirements bias. So requirements bias is essentially where your cognitive biases get codified into system requirements. So an example of that would be asking for a classification system to be built to tell you someone's sexuality or gender when these are non-binary construct or currently considered non-binary constructs. So this is just a sample of some of the types of human cognitive bias and how they can arise in people's minds. We also have data bias. So data bias can have a lot of different causes. The biggest one is not having representative training data. AI systems are only able to do things that they have seen done in training data. The error rate, as soon as you go out the boundary of the training, increases dramatically. So a lot of the work around bias is about non-representative sample data, and I'll talk a little bit more about how you actually go about checking that data shortly. Confounding variables. So confounding variable is having a variable that influences both the dependent variable and an independent variable. So essentially, you've got something going into the model that is correlated with the outcome. So then you'll get a bias in its future predictions. Non-normality arises from where you're assuming a normal distribution on data that turns out not to have that kind of distribution. Data labels and labeling is a huge one. As I'm sure you know, when you are doing a capture and telling Google whether how many palm trees there are in a picture or how many traffic lights, you're helping to train systems. A lot of companies will outsource this. So let's say I want to build a system to tell the difference between, let's say, an SUV car and a minibus. Okay. Now I might obtain millions of pictures or thousands of pictures of SUVs and minibuses, and I might send these off to low-paid workers, often in other parts of the world, that will manually go through them and annotate them with labels. And this label will tell me whether it's an SUV or a minibus. And then I can use that as supervised learning training data. But the problem I have is, do I know that people are applying those labels consistently? So SUV is an American term. Maybe people interpret SUV differently and hence apply incorrect labels. Or if you take something around people, maybe people's cultural kind of norms are different and that affects their labeling. Maybe they're just not paying attention and just hitting OK on everything or hitting a default label on everything because they want to get the money and go. So data labeling is a particular issue. You also need to consider missing features. So missing features is an interesting one. Essentially, machine learning models don't handle null. They don't handle blanks, right? So if you have think about a table of data, and let's say your labels are missing or are more likely to be missing for certain groups of people, or values tend to be blank for certain groups of people. So that will directly affect the training. All the data with intermittent blanks will be dropped and deleted. And if those are missing predominantly for certain groups of people, that will directly affect the representativeness of the data. Data processing is another issue. So a lot of people will rely on data scientists to do a lot of this work. So the way a data scientist works is they have some kind of local environment, they have a data set, and they have some Python or some other programming language. And they're going through and looking at the quality, and they might look at it from a bias perspective. But the output of a data scientist is a trained model. There are many other things that go into a running system. So I've got, traditional software code is extracting data, pre-processing data, feeding it into the model, and then the outputs are going off somewhere. In fact, that is 80% of the work on implementation of a machine learning project. Is the data processing. Now, just normal software bugs can influence the data that then hits the model. So for instance, you may have a bug that is some combination of types of people that data gets changed or is missing. And that can then cause bias in the process. So you can't sit there with a data scientist and prove there is no bias in an AI system, only in a model. It's an important distinction. Data aggregation is another issue. Perhaps you are aggregating different data sets that were collected through different methodologies or have inconsistent statistical properties. And distributed learning. So distributed learning is running machine learning on in lots of instances that are distributed. So on my Android mobile phone, I have a machine learning model, which is a distributed machine learning model, and it's on every Android phone, I believe. And it looks at when I go to bed and when I charge my phone, and it optimizes the charging process. So because of the way batteries work, it's optimum for the battery to start charging an hour before I wake up, or to slowly charge overnight and then burst like an hour before I wake up. And that model isn't trained by Google. They have taken a model and some hyperparameters, and it's trained based on the data, on my data on my phone. And that could be great. I mean, that means there's no bias. That algorithm is purely trained on my behavior. There is no bias there. But if you are using distributed learning and covering a much larger group of people, rather than having one bias problem, you might have 10 or 100 bias problems, and you might need to do all this verification and validation in lots of different ways to try and minimize the risks. Bias can also be introduced by engineering decisions. One of them is feature engineering, the decisions you make. And for those of you who don't know what feature engineering is the process of determining which data inputs you're going to give to the model. And you may do something called imputation in that process. You may try and fill in some of the blanks I was talking about before by making guesses. Additionally, just that selection of features is pretty key. If you have what I call a protected category variable, so something like race, gender, then you might need to make a decision about whether you actually use that, because there's a very high risk of introducing bias if you use such variables. But taking that variable out doesn't solve the problem, because many other things are correlated with these protected category variables. If you think about something like shoe size might be different for people of different races. In fact, in the UCAS example that you before, it's the way people write, that's kind of being correlated with their race and then causing these issues. Algorithm selection is another issue. Different algorithms have different levels of bias, essentially. hyperparameter tuning. So hyperparameters are things that you do before you train the model, and tweaking those values in certain ways can either introduce or mitigate bias issues. There's also model interaction, right? So typically you're not dealing with a single model. If you look at something like facial recognition, you're dealing with an algorithm or model that segments the face, and then a different algorithm or model that recognizes it as something or someone. So the interaction between these models and how expressive and informative they are in their interactions with each other can also introduce issues. So three main groups here of where bias comes from. It comes from human cognitive biases. It then ends up in data, and it also affects engineering decisions. It is possible to have data issues that don't relate to human cognitive bias, and they just appear. So things like outliers and noise in the data that aren't related to any human bias can also cause certain types of data bias. So here's a slightly different view on this. So this is from a paper that I didn't mention at the start, actually. So I'm director of a not-for-profit called For Humanity, which is looking at how we optimize AI systems for humanity. And this is part of a paper we released last week about how you can take just your training data and examine that for bias risk. You can find this paper on, I think the URL is a bit later in the pack. So at the conceptualization stage, you might find techno-solutionism, finding the technology and then trying to find a way to apply it. You might have issues with cultural values and stereotypes, social constructs and groupings, and decisions on protected categories. All throughout your process, you need to think about who your team is. I'll give an example of this. I've been in one meeting where we've been looking at potential bias risks in banking, in financial services data. And somebody from a not-for-profit that represented a particular low-income group was able to flag up the impact of being a seasonal worker and how that might affect the data set and how that might then lead to unfair outcomes. So having people from different backgrounds, it is quite important. This is not just a data science issue, as I'm sure you're all aware. In our data collection and processing, which is a very, very important stage, we need to select methods. We need to look at things like aggregation and imputation, as I was talking about before, combining multiple data sets, and these can cause issues. In design, development, and validation, we have another set of ways that you can inject bias in your solution. Implementation and monitoring, this isn't just a one-shot thing. Increasingly, large ML implementations don't just have people managing the infrastructure in their IT support teams, they have data scientists doing constant monitoring. You have things like adversarial attacks. So adversarial attacks are ways that you can compromise a system from the outside by feeding it certain data. That can cause bias as well. I think the biggest example of that is probably Microsoft's Tay bot. It launched on Twitter that had to be shut off within like 24, 48 hours because Twitter users were saying things that were influencing it, and it became politically incorrect very, very quickly. Concept drift is another important one. The correlation between inputs and outputs changes in the real world with the evolution of time. Conscious of time, so I'm going to move on to the top things you should do in any kind of implementation project in order to mitigate the risks of bias. The first thing is to gather external requirements. So things like GDPR, things like EU regulation, to understand those requirements and to understand the stakeholders who are responsible for those within your organization. The second thing is to gather internal requirements. Perhaps you have a corporate social responsibility policy. Perhaps you have a risk management policy. Perhaps you just don't want a biased system because you want to protect your reputation, right? Both Amazon has come under a lot of fire in the press. Google, these companies invest a lot in trying to avoid those situations. Identifying stakeholders is a very important step. By stakeholders, I don't mean the people that pay for the project. I mean people who are affected by the outcomes of the eventual system. Establishing thresholds and acceptance criteria is a crucial step. When you start a project using AI, you don't really know how well it's going to work until you've done your first experimentation and looked at your first data. To avoid confirmation bias, you should decide up front what is an acceptable accuracy level. Is 90% accurate enough? Is 80% accurate enough? What are the groups that might be at risk? And how can you, what is the different thresholds that you want to apply to those groups? I've talked about transdisciplinary input. That's really important. You wouldn't see a data scientist being able to run through all the processes I'm talking about. Oh, this is something that involves all sorts of different disciplines and professions. Carefully selecting and documenting your data sources is very important. As you can imagine, if you trained something based on pictures of people available on the internet, you would see a bias towards countries which use the internet most heavily, probably the West, right? So taking data from public sources is risky. In fact, there's a whole load of data sets that are called benchmark data sets, which are used for all sorts of things that are industry standard. There was research a couple of months ago that found there was a 3.6 label error rate on average in those data sets. So even data sets that are held up as benchmarks can have issues. So you need to think carefully about selecting those data sources, document the chain of custody of the data quite carefully. So these are the things you can do right at the start of your project before you potentially even hired a project team. Then we move on to design and development. So as I mentioned before, labeling is a crucial issue here. So having protocols around that process is important. And that might be a protocol to make sure that you provide appropriate guidance on how to do the labeling. You define SUV properly. Or it might be a quality management process where you sample check 10% of the labels from each labeler. There's also a number of things that you can do in the feature engineering space. So I won't explain these 4 techniques, but essentially they allow you to understand the relevance of different features and to try and optimize your model. And these can be quite useful in the feature engineering process to try and make that decision about dropping certain features and analyzing how those features correlate with other things. In the training and tuning stage, you can do various things as well. So upsampling, first of all, is increasing the amount of data you have about underrepresented populations. And this can be done by going and getting more data. There are also synthetic data methods where you can actually use machine learning to create more data, which you then use to train another machine learning model. There are model-based methods that essentially put logical constraints upon the outputs of a system. There's something called a joint loss function, which will automatically penalize biased results or results that are perceived as biased results. Decoupled classifiers is a technique to train a classifier in each group. So for instance, I have one model for women and one model for men. And finally, transfer learning is a technique that can help mitigate the problem where there's not much data available about certain groups of people or objects. So this is the design and development stage. So this is where your data scientist is working on the model, or somebody's going and gathering additional labels. Now, I'm going to call this a stage, verification and validation, but in a modern agile environment, it isn't so much a phase or a stage, it's an activity. So the first thing you can do within verification and validation is you can analyze your training data. Static analysis is where you analyze a computer system without running it, essentially. So the paper I mentioned before is actually linked at the bottom. This paper is probably, in my view, one of the, I helped write it, but it's one of the most exhaustive lists of things you can do in this static analysis activity. The first thing you can look at is there a protected category variable as a feature? You can also look at whether other features correlate with that. So I gave the example of shoe size earlier. Another example would be postcode, correlates with socioeconomic class. Is there enough data associated with each PCV group? If I figure out I've got these six groups of people that I'm worried about being biased against, do I have enough data relating to each of those groups of people for a system to be unbiased, or system have a chance of being unbiased? Now that breaks down to a range of sub-questions. What are all the different possible values or ranges? Do I need to figure out all my different groups of race and ethnicity? I need to understand statistical significance here, because I need to understand whether I have enough data for each group, and that becomes very complex in its own right. I need to understand whether features are present consistently. Like I said before, if there's missing data or nulls, that can affect the training process. The supervised learning is what I'm trying to predict, available with a similar frequency for each group. I also need to look at whether my training and testing data sets are collected using the same methodology, and whether they have the same statistical characteristics. And then finally, I need to look at whether my labels are reliable and consistent. So this is quite a lot of work, and you can do this without having built a model, just by looking at the data that you're planning to use. And doing these things on the screen will probably have the biggest effect. However, it doesn't tell you everything, because there's lots of things other than the training data that can affect bias. So other things you would do as part of a verification and validation activity, first of all, not just model testing. So not just data scientists testing the model. It has to be an integrated test, potentially even involving users. So users can give you a whole other insight on the system when you actually integrate them with it. Internal validity testing is essentially testing based with the data you have. External validity is going and getting other data. So lots of the literature that demonstrates bias in live systems uses data from, say, a census. So data that they're correlating zip codes with demographics, for instance, with Amazon Prime delivery pricing. And then they're demonstrating that you're more likely as part of a certain demographic group to get a different price. And this has been shown with Staples as well, in terms of their pricing, the differential pricing they offer on their website. And then we deploy the system. And there's a number of risks in the deployment of the system that we need to keep an eye on. Now, one way to do this is to put a human in the loop. So a human in the loop is where a human approves a decision that's recommended by an AI system. One interesting thing about this is, due to another type of bias called automation bias, human decision-making degrades by 5% at least when AI is making a recommendation. There's another phrase, human on the loop, which is where a human is watching the system, but is not required to approve decisions. An example of that would be a self-driving car, an autonomous car, where a human is supposed to be watching for incorrect decisions and taking control of the car if it makes the wrong decision. Because bias can continue to change after the deployment of a system, you need continuous monitoring. So examples of that are reinforcement learning or regularly retrained models, which are retrained in a production system. Now, the bias can increase or decrease dramatically with each iteration. And as the system changes, you need to keep monitoring it keep monitoring it. Transparency tools are also very useful at this stage. So Google has model cards, and there's other frameworks from other big vendors that are essentially tools for being transparent with your users and stakeholders about data. And interestingly, that's one of the requirements in the EU regulations. It is that full information is provided to end users of AI systems which are sold, including lots of transparency about the data and, in fact, the resulting accuracy. And finally, training, not in terms of model training, but in terms of training people and teams. You need to train people to understand and watch for these issues, which again is very difficult at the moment because we don't really have technical standards that formalize what I'm telling you today, or they haven't been finalized, and hence there isn't many training courses and things like that available. Okay, so that's the end of my talk. My email, Twitter, and LinkedIn is on the screen. I'm always willing to answer questions on this topic offline, but we have about 12 minutes now if anybody has